So let's now look at the equation for a batch reactor, which was derived earlier, and so we've got our agitated batch reactor, which has volume V, cubic meters, and it has a starting component A, which is Ca moles per cubic meter. Well, that's its concentration. Now the expression which was derived previously was that Ra, the reaction rate of A, is equal to the rate of change of Ca in the reactor with time, dCA by dt. So what we're going to assume first order kinetics for this reaction rate. That is simply that Ra equals minus K times Ca. So we've got first order reaction in our starting component A. And we've got that K is the kinetic rate constant, the first order rate constant. Because it's first order, it has units, seconds to the minus 1. This is negative because the reaction rate is negative because Ra is a starting material which is being consumed. So we've got Ra equals minus K times Kca. And if we substitute that into there, combine the two equations, we get that minus K times Ca is equal to dCA by dt. Now I've got to make a further assumption in order to integrate that expression. And that is that we've got constant temperature, or at least that the temperature is close enough to constant that our value of K can be assumed to be a constant. And so if K is constant, then we can integrate this expression, and we get minus K times integral dt. We call it integral dCA over Ca. Now we need to have some limits on these integrations, so we're going to integrate from time t equals 0, at which point, so that's the starting point of our reaction. So we're going to assume that we've got a starting concentration of our component A of Ca0, and that's at times t equals 0, and then at some time t, the concentration at A has gone down to a new value, Ca. So we can integrate that, and we get that that's an easy integration. So K is constant because of that assumption we've made, and you've got minus Kt between limits of 0 and t. An integral of 1 over Ca dCA is log term, log of Ca, and again that's between those limits of Ca, Ca0 and Ca, and that gives you minus Kt equals log Ca minus log Ca0, which is simply the log of Ca divided by Ca0. And if you want to calculate the required time for a given final concentration, so your batch reaction time to achieve a final concentration of Ca, then you could just rearrange that slightly. Take minus k over to that side, divide both sides by minus k, you get that equals t equals minus 1 over k times log Ca over Ca naught. And it might be quite convenient just to get rid of that minus sign. That gives you 1 over k. So if you take that minus sign in there, you can invert the log. And that gives you Ca naught over Ca. So that's an expression for the required reaction time to achieve a final concentration of Ca from an initial concentration Ca naught if you've got a first order kinetic rate constant of k. You can go back up here though, and you could take the exponential of both sides of that equation in order to get rid of the log, and that gives you exponential minus kt is equal to Ca over Ca naught, and that gives you that Ca is equal to Ca naught times our exponential minus kt. And that's the expression you would use to calculate the final concentration for a given time from a known starting concentration, and that's a typical first order exponential decay of your starting material.